morning, students. Today I am going to talk about the spiral structure of Milky Way galaxy and the active nuclei or galactic nuclei of the Milky Way galaxy. As you know, Milky Way is a Milky Way galaxy is a spiral galaxy. Now, in 1976, Y.M. Georgelin and Y.P. Georgelin they determined distances of different H2 regions. H2 regions means ionized hydrogen, means single proton, by radio and optical observation. By observing the radio emission from, as you know already, from neutral hydrogen, molecular hydrogen at wavelength, radio wavelength 21 centimeter, the astronomers now have a clear picture about the structure of the Milky Way galaxy. Now, from these observations, it has been confirmed that, the four-arm structure of the spiral arms of the Milky Way galaxy can describe the observed phenomena that is what we are observing in the direction of the Milky Way galaxy can explain. And the rotation of the spiral arms is rotations are clockwise. Now, in the first picture you have seen the artist impression of Milky Way galaxy. Now, I will draw more scientific, means what scientists observe, not artistic. Scientists observe about the spiral arms of the Milky Way galaxy. There is a center called galactic center. We will discuss about the galactic center later on. Now, if you as you turn to be here, and we assume that we are seeing the galaxy from upward, that means from north galactic pole. Observers point of view is, then the arms are like this. This is the first arm. Second arm. Third arm. Fourth. Our sun is there is the sun. This is galactic set. So this direction will be, if you measure longitude, this direction will be represented by 0, and other angles. This direction will be 180 degree. This direction will be 0. This is 90 degree. This will be 270 degree, of course. 270 degree. This will be say 50 degree. So this is the picture that we are of the spiral arms that we see. The spiral arms are this way. So the galaxy is rotating this way. So galaxy is rotating clockwise. If it is not rotating clockwise, then this spiral structure will break down. Now, this spiral structure, how this spiral structure is produced and maintained, there is a big debate. As I have mentioned, I have pointed out that if the spiral structure is like this, and we have already said that the rotation of the Milky Way galaxy from Woods analysis that there is a differential rotation. Now, this is a structure stretched out in space. If there is a differential rotation, then obviously this structure will break down. Because if this point is rotating with greater velocity and this point is rotating with less velocity, then this will come close to this uh, by that time. By that time it will be there. So this structure, I mean, if it is not rotating, if it is not rotating as a solid body, then any structure stretched out in space cannot be maintained. So there is a problem. How this spiral structure is being maintained. There is another problem, how this spiral structure has been created. These two problems are interrelated. Uh, some speculated that there is if there is small perturbation for unknown reason in the galactic center, then that perturbation is stretched out in space and causing the galactic arc. This was thought by the astrophysics scientists that this may be the origin of spiral structure of the galaxy. But soon it was realized that if that is the reason for creating any disturbance from the center for the spiral structure, then for a few rotation, galactic rotation, because the galaxy is rotating. After a few galactic rotation, a spiral structure will be faded. So these two things are contradictory. However, there is a theory now most people believe it to be or think it to be correct. That the theory is called density wave theory given by C. Lane and H2 in 1960. And their theory can explain many observed phenomena in the galaxy. The theory, in a nutshell, the theory is like that. There is a density, wave-like variation of density in the galactic disk. The density of the galactic disk has a periodic variation, means wave-like variation. Somewhere the density is greater, somewhere the density is less, and there is a pattern: greater, less, and this wave-like variation in the density. This pattern, this wave-like variation, this pattern rotates as a solid body. Otherwise, if there is a solid body, then the wave-like pattern radially outwards to the center will break down. It rotates as a solid body. Now, as matter passes through this, as gas molecules, matters passing through this wave-like density distribution, when it comes to the denser region, their gravity becomes active and the clouds compress to form stars. Since most of the active nucleus and the molecular clouds H2 regions are found in the spiral arms, this theory can explain the observed uh, objects, young objects like molecular clouds, H2 region, and bright young stars are spiral arm. Generally, spiral arm contains new stars, bright stars, because we believe that, thought that the new stars are formed in the spiral. So density theory by Q and Lee can explain many things. Though why there is a question. Next question is that why there will be density which is varying with weight, varying like weight. It states. So spiral structure of the Milky Way galaxy is like this. If we assume there are four arms, two small arms and two big arms, then observed phenomena can be explained. Now I will discuss about the galactic center. This part. Now I will discuss about the galactic center. Now, what is the necessity for starting galactic center? The reason is that the galactic center is called the active nuclei of the galaxy. It is a very active region. Now, what is happening inside it is unknown, because we cannot because the in the optical region we cannot see what is happening there, because there is dense molecular cloud and dust, so it prohibits, it blocks our direct vision. But there are indirect ways to see the galactic center. But before that, there is an important thing. After the observational techniques and instrument improve, first we have divided the stars in the Milky Way galaxy into two types: population 1 stars and population 2 stars. Population 1 star are young stars, which are huge in number, which are found in the spiral arms or in the galactic disk. And there is population 2 star, which is found in the halo region of the galactic Milky Way galaxy, which were generally in globular cluster form or in open cluster form. And this classification was based on their position, not only on their position, based on their age of the stars and the elemental abundance of the star. It was found that the population 1 stars contains more metals, and population 2 stars are there is very little or in fact no amount of heavy elements. And another thing is that population 1 stars are actually young stars. Their age is small compared to the population 2 stars, which stars are the age of these stars are very old. In fact, some of the stars are uh, age of the galaxy itself. So based on these criteria, this division was done in the stars of the Milky Way galaxy. But later, it was found that there are an intermediate class of galaxies, class of stars. So the initial idea of the classification of stars into population 1 and population 2 or population 3, it does not work. There is no obvious reason to why. Then suggestion came that we should give the new class, the intermediate class, a new class, and their elemental abundance and their age is such that they cannot be put into the population 1 star and population 2 star. Now this population is referred to as big galactic disk population. This is a disk galaxy, so we consider the disk means its thickness is very small compared to diameter. But in the thick galactic this configuration, there is a region galactic center where the thickness of the disk is high, is greater. That is called thick disk. And most of the intermediate stars, the new class of stars, are found in this region. Now it has become clear and we will see it in the later class when we see the classification of galaxies, different types of galaxies. It has been clear. It has been now clear that all the spiral galaxies, in all the spiral galaxies, thick disk is a universal feature. There is a thick disk in the central region, and this thick disk actually is of interest for study for the astronomers, because it will reveal many interesting things that is happening inside the galaxies, and there may be some active galaxies outside the Milky Way galaxy. And to know the properties of the galaxies, active nuclei, we should study the nuclei of the Milky Way galaxy. In the same way, when we study stars, we first study sun, because sun is very close to us. And the study of the behavior of the sun will reveal many things about the behavior of the stars, distant stars. Now, in 1971, W. Sen showed that the motion of the hydrogen gas could be explained if there is a central bar pointing about 20 degrees away from the direction of the galactic center. Now, as I have already said that our galaxy is the galaxy is a barred galaxy, means there is a bar. Now, the presence of bar was first pointed out in 1971 by W. Sen, who made extensive observations about the neutral hydrogen gas, means radio wavelength 21 centimeter, radio waves of the wavelength 21 centimeter, and he observed the motion of the gas, and based on his observation, he proposed that this the motion of the gas inside the galactic center would be explained if we assume there is a spark. And later, the Kobe satellite, which was initially was launched for monitoring or tracking the microwave background, and its small variation, but it also mapped with the sky with infrared wavelength dominated by light of pole star, and an asymmetry was found, and that asymmetry could be explained with a bar of axis ratio 0.6. Later confirmations of the existence of the bar has come from mapping of the central distribution of pole stars using near infrared photometric distance. So recent observations also point that there is a bar in the central region. Now, as we approach to the center, the density of the stars is increasing, continuously increasing, moving towards the central peak. But there is a twist. The twist is there is a central hole of radius 3 kbc inside the thick galactic disk. That means there is a region where you can find nothing. There is no interstellar gas, there is no star. So there is a hole of radius 3 kbc. Now, this may be due to the reason that the since due to the nuclear galactic due to the power of the galaxy, since power is also rotating, so it will drain away the gases to the nuclear center. So the galactic center of gases will be directed to the center. So there will be a reason where there you cannot find any neutral gas. But all is not in. Inside the central core, there is a dense nuclear gas. There is a distribution of gas inside the nucleus, which is increasing and starts, which is increasing as we are moving towards the center, like this. Here the density is increasing towards the center. Then there is a hole in which, in this region, this density is increasing in this region for a distance like this. There is no density of stars. There is no stars and the density of matter is very small. So we call this hole. Inside the hole of the radius of 1.5 kbc, just hydrogen, there is thick, there is a dense nuclear gas. And its mass is molecular and concentrated within 300 pc of the nucleus. But its mass is molecular and total mass is concentrated in only 300 pc of the nucleus. And mass of the nucleus, mass of this region is 300 pc. 300 pc. Mass is 10 to the power 8 solar mass. This mass is 10 to the power 8 solar mass. That means 5% of the total mass of the Milky Way galaxy in a very small region. Now, one theory is there: the molecular clouds are probably confined. Here, the molecular clouds are near confined by the pressure from the surrounding very hot gas. In the surrounding, there is a hot gas outside, and it exerts a pressure. That pressure may explain the molecular gas of high density inside the region. And this dense gas, hot gas, may expand vertically, considering the horizontal plane, and it may expand in the vertical direction, forming galactic wind. So gas is lost. The gas lost to a wind or to a star formation, the star are formed there, is replenished with the infilling gas of the larger radius. Outside the region, there are gases which are coming inwards, and some gases are going out perpendicular to the direction in which it is coming. So there is a balance. Now we come to the very close to the nucleus, galactic center, which is Sagittarius A. Now we come to the 300 pc to 10 pc dimension. Inside the 10 pc region, it is only 10 pc compared to the 3 kpc of the nucleus, galactic nucleus. 3 kpc diameter is radius region is called galactic center. And now we come to the very close to its center of radius 10 pc. And this region is dominated by radio continua source and we call it Sagittarius A star. The SGR A star, which is a source of continuum radio source. Sagittarius A star is named because it is a intense source of radio wave, and the source is continuous. Basically, our knowledge of the center of the Milky Way is based on radio and infrared observation. In the optical region, the view of the center is blocked by the dark clouds in the Sagittarius spiral arms about 230 miles. If there, the study of galactic center or nucleus is important because it may be a small scale version of a very much more violent activity of a active nuclei of some external galaxies. It therefore provides opportunities to study close hand in the same way as our sun does for the study of other stars. Since active galactic nuclei are thought to contain black holes with mass larger than 10 to the power 6 solar mass, there may also be a large black hole in our galactic center, as evident in the discussions that follow. Now, the high resolution observation has revealed that the size of the intense radio source is now also small, very small, 0.3 AU, means one third the distance between Sun and Earth. Very small region, the source of radio waves, and its luminosity is tremendously high. Luminosity is 10 to the power 6, 10 to the power 26 joule per second. It is a tremendous luminosity, but not in visible region, in the X-ray region. Now, powerful techniques of observation made it possible to resolve individual stars in the galactic center. This is a very recent observation. This powerful observation made it possible to resolve individual stars. Now, the astronomers discovered that the stars are moving in elliptical orbit within Sagittarius A star as a common focus. Now, inside these stars are moving in elliptical orbit, all in all directions. The stars are moving in the elliptical orbit. So the case is similar to the planets revolving around the sun. Now we can use Kepler's third law to find the mass of the central region above which is assumed to be black hole. The mass can be determined. Among the many stars spotted, three stars are important because their orbits are quite clearly resolved, and their orbital parameters could be measured very accurately. So I am listing only three stars in the galactic nuclei done by Hayes and Gilson. This work is done by Hayes and Gilson. relation. Number one star, it has a time period T equals to 14.53 years. Yes, and semi-major axis A equals to 919. This is semi-major 919 in astronomical unit. Second star, the time period of 36 years and semi-major axis 1680. Third star is 37.3 years and its axis parameter is 7, 7 These three stars, the parameters, orbital parameters, that means time period of evolution, and their semi-major axis has been determined very carefully. Now, using Kepler's third law, there is a relation between semi-major axis and time period, and the relation is, we know the relation is T square equals to 4 pi square A cube by A. Right? This is Kepler's third law. So from which we can say that M will be equals to 4 pi square A cube by G into T square. Now, reading of the parameters of the first term, the value will be 4 into 3.14 square A cube, means 919 into 1.5 into 10 to the power 11. One astronomical unit 1.5 into 10 to the power 11 meter cube by G is the universal constant 6.67 into 10 to the power minus 11, and T is the time period 14.53 years. So into 3.16 into 10 to the power 7 seconds square. So this is the value. If we calculate this thing, then the value comes out to be 7.3 into 10 to the power 36 kg, which is in terms of solar mass 3.6 into the power 10 to the power 6 mg. That means 3.6 360 million times the mass of the object about which the stars in the galactic center within very small 30 pc radius is revolving, though this radius is somewhat greater than this. So there is a very small region from where intense X-ray of huge luminosity is emitting, and which the mass of which is 4 million times, 3.6 million times the mass of the sun. Now, what could be the thing which the dimension of which is very small, 0.3 astronomical unit, and so massive? So, the best plausible answer is the black hole. If indeed it is a supermassive black hole. next class we will discuss about the different galaxies. We'll see that most of the galaxies contain black hole, supermassive black hole center. Now I am giving homework to you. Calculate with this same method. Calculate the mass of the supermassive black hole using this orbital parameter of star 2 and star 3. See whether these are close to this or and giving it as an exercise. Do it. Thank you.